Hello and welcome everybody. Today I'm going over Module 1, Lesson 6, which is titled Fitting Lines to Data Points, Modeling Linear Functions. What we're going over today is regressions, specifically linear regressions. And by the end of this class, we're going to go over 6 different types of regression. So if you know how to do linear regressions, it's going to be hardly any different when we move on to quadratic, exponential, log, quartic, and cubic regressions. Okay, so this is kind of the first building block to many more regressions that we're about to do in this class. To prepare for this lesson, you need to know how to use function notation, and you need to be familiar with your Desmos basic features. And then from last lesson, you need to make sure you know how to solve equations graphically using the intersection method. Our learning objectives are to create a scatter plot for sets of data, to visually determine whether a set of data can be modeled by a linear function, find approximate linear models for data, determine whether a linear model is, quote, a good fit for data, and as always, apply real-world information. As a reminder, you can pause and rewind this video as often as you need, so this lecture is at your own pace. I'm guessing you already scanned this QR code to find this lecture video, so thank you for doing that. And then you need to look at your course calendar to see when this lesson's homework is due. I want to go ahead and actually just turn the page. And I want to do an introduction of what a linear regression is here. I have your definition of a linear regression, and that is the procedure to determine the equation of a line that is the, quote, best fit for the set of data. Okay, so here are some examples here. And we actually did this a little bit, I believe, at the end of lesson 2, where you had to make a scatter plot. We're going to do that again in Desmos, then type in the equation, and you kind of saw the line of best fit there. Now today we're going to be coming up with that equation for the line of best fit, but it's not too bad as long as you know how to do it in Desmos. So we have some different examples here. And so what we're looking for is more of like this strong positive correlation or the strong negative correlation. You can see with both of these that this equation, this line, is hitting most of those points pretty accurately. So it's a pretty good representation. Same thing with this. There's more points here, it looks like, but all of those points are pretty close to that equation, or again, that line. You get weaker ones when you can kind of see how those points are making a line. It's just they're so scattered, right? So we can still make an equation that is the best fit for the data, but you can see it doesn't really model it super well, because like this point's way off my line, this point's way off my line. So this is a pretty weak correlation. Same with this one. And here we have a little bit more of a moderate, where these strong ones, all of these points almost touch that equation here. They're a little bit further off, but you can see it's a little bit more clustered together than, let's say, this one here. And we won't have any like this, but this one here would be an example of no correlation. Those are just completely random points. I can't say that could be modeled by a line, a quadratic, any kind of graph there. So this would be no correlation, but most of ours will probably be strong, positive or negative. And this one's positive, right? Because this line has a positive slope. This one's negative because it has a negative slope. So what we're going to be doing today is graphing these scatter plots and then finding the equation of that line.